Okay, so to start here, we're going to talk about distance, rate, and time, or distance, velocity, and time, and what the integral does for us with those. Okay, so if you have a sorry, that's not. This needs to be velocity. Okay, so we have time versus velocity graph. This would be something like that. Okay. Let's say your velocity is constant over a given period of time. How far have you traveled? Okay, so let's say my time's 3 hours and I traveled 60 kilometers an hour. How far did I travel? Learn how to multiply, Ben.
180.
Thank you.
I'm sorry.
Okay. Here's the nice thing about this. If you have a rate and a time, that value right there is in fact the amount of area in that rectangle. Okay, because it's 3 wide, right? The rectangle is 3 by 60. Okay, so the area is the total distance traveled. You can also get into where it's not just one big block of time. Okay. How would I calculate distance traveled on that one? Yeah. Yep. Okay, so calculate each area, add them up. I think you got the concept there. Now, when we travel, do cars start, stop, and accelerate instantaneously? No. They do not. So what do we have? We have curves. Okay. Can we accurately use rectangles to represent that area? No. We have to approximate it. Okay. So what we're going to work on today is approximating area of curved graphs. Okay. So I would have to do something like this. Thank you, Ben, for the compliment. Okay, so that would be a low estimate of the distance traveled, correct? All right, so we could also do a high estimate of the distance traveled. Our goal here, and what an integral actually shows us, this is where we're headed. The integral gives us the exact area Okay, so if I can take the integral of a velocity function, I will get the exact distance traveled. Right? That's where we're headed with it. The question is, what is an integral? Okay. Which we're not going to get to today. We're just going to be approximating today.
Everybody catch the
I'm pretty sure I don't care about that right now, Ben.
No, usually.
Get some colors. Okay, so let's say that that's my velocity function. Okay, so I have a velocity function. Is that a high or a low estimate of the distance traveled?
Low.
It's high because we're above the graph. Okay.
Okay.
These rectangles, this is key here. These rectangles, see how those are on the right side of the rectangles? Okay, this is called the right endpoint approximation. Okay, because the rectangles on the right side hit the graph. Okay. We're going to focus on the right endpoint today. You can also do left. If we did left endpoints here, it would be a low approximation, right? And we could also do midpoint approximation, where we do the middle of the rectangle. Okay, it would be pretty close. We can also do trapezoidal. Okay, so there are several different ones. We're just going to hit one today. If I wanted to do the work here, there's a little formula if you want to use it. Let me. Okay, what's the change in our x value here? No, it's our time, but what does that change by on my graph? By 1, right? So that's the change in x. 1. Okay. And then A is 0. Yeah, A is where it starts. And you know that change in x is 1. So what's f of 1? Is 10. Plus, and this one's f of 0 plus 2. What's f of 2?
What is A?
A is the starting value here, 0. Okay, f of 2 is 10. No, sorry, f of 2 is 20. And f of 3 is 40. And then we're done. 30, 70, Okay, and we didn't specify units.
We have to do 40 as well. We have to do after 3.
You have to do all intervals, yeah. So this formula allows you to avoid doing every single rectangle separately, okay? Because our x value, the interval is the same. All right, are you okay with that?
What is the R mean?
Where?
Like what
Oh,
problem solve for?
that's the right-handed with n intervals. This has 3 intervals, right?
Oh, it's saying the value of the.
And this is right-handed. So right-handed with 3 intervals.
So let's talk about the top corner.
And n would be the last, so it'd be a to n, or sorry. N would be the number of intervals here, 3. A is the origin. Yeah. I should have specified that a little better, huh? All right. Let's do one formally. Calculate R4 for f of x equals x squared on that interval. Low blood sugar, huh? Yeah, it's a curse.
I have to wait 3 years to be diabetic because they're making these like just look.
Why do you want to be?
No, I
Trust me, it sucks.
I know it sucks. I don't want to be, but if I am, I have to wait 3 years because they make me like temporary tattoos and they make cover your skin and have like little like computer like chips in it. So they give you a shot.
Wow.
Oh my god! So you don't give yourself a shot. It's just a little tattoo and you take off.
Okay, so I guess let's draw the picture here. Okay, if that is x squared, right? I want from 1 to 3. I need 4 intervals. So yes, we want 4 subintervals. No. Okay. To calculate how big those are, 3 minus 1 over 4. Okay, so we know that each of them has to be 1/2 of a unit.
Then why in the last problem did we have 3 intervals and we had R3?
Because
Okay.
it's R3 is the number of intervals, not the size. They're not 1 unit each.
Okay.
They can be different. Okay, so we have 4, right, rectangles that are 1/2 a unit each. And you can see on my diagram that they hit the top right corner of that rectangle.
So, is there a formula for calculating the size of the interval?
Yeah, I just gave it to you. It's
It's 3 minus 1 over 4.
B minus A over N.
Okay.
Yeah. All right, so we're going to use our formula here. What's the change in x?
3.
No. Right there. That's the change in x.
So where did you get
1/2.
4 of those things from?
4.
Oh,
R4.
well,
Right-handed
maybe.
with 4 subintervals. Yep. Oh, never mind. I'm going to keep my mouth shut. So our formula is change in x. So that's 1/2 f of a plus delta x. In our case, it's 0 or 1 plus 1/2. Okay, do you see where I got that? Anybody? Not?
We know.
Okay. The next one, f of 1 plus 2 times f is 1. So f of 2, f of 2.5, f of 3. Right? We got to the end of our interval here. With the right-handed endpoint, that's going to be the last one. If you're with a left-handed endpoint, the last one's going to be that one. Okay, what is f of 1.5? Yep. So you can do that math. 6.2. Yep. So that is the area of all 4 of those rectangles. Okay. It's a high estimate of the area underneath the curve. That's the area under the curve. It's above it. Okay. I hope it is. That's why we're starting small. Do you have any questions? You're okay calculating area? Do you need me to talk about the left-handed endpoints at all? It's the same thing, you're just doing it on the left. Yeah, so your left-handed, if it was L4, it would be f of 1 plus f of 1.5, f of 2, f of 2.5. Do I need f of 3? No, because that's 4 spots. We don't count the right side. Okay, so be aware of the left-handed endpoints as well. Okay, let me write the work down. Do you want me to write all 3 days down?
Would the equation be, would A be?
It would be f of a
So it'd be 3 minus.
plus f of a plus delta x plus f of a plus 2. No, a is still the same. The question is, do you include it? For left-handed, you say f of a. For right-handed, it's f of a plus delta x. So it just shifts it to the right, one interval on the right-handed one.
So it's just A. Correct.
Yeah. Yeah. Okay, here are the problems. They should be up there on the board too. Here's part A. B. C. Spiral. We're starting in the AP4s now as well.